The webinar is enthalpy versus heat recovery. The technology, the differences between the two solutions, and the benefits for enthalpy and then for the heat recovery as well. The targets for the presentation. Yes, the targets then. With this, let's say, webinar session here, we want to discuss what are the benefits of enthalpy recovery, what are the differences between the two different heat exchangers, and what can you gain from one or another solution. Also, we want to talk about when does it make sense to use enthalpy recovery, because we are living in, as we can see, a very international audience, that we are living in different climate zones and therefore different environments, and we want to see the results there. We also are talking about the energy savings with enthalpy solutions, and does it have an effect, and is there energy saving in this way? And also, how does enthalpy recovery work? What are the functioning and the principles of this heat recovery solution? Or, sorry, heat and enthalpy recovery solutions. Yes, so the definition of enthalpy recovery is that, and also one point that I want to bring out in the beginning of this webinar is that today we are focusing on counterplate heat exchangers only. And in this way, for Zehnder and PAL ventilation units, we are defining the enthalpy recovery solution as ERV, enthalpy recovery ventilation. In the, let's say, energy recovery world, it's also used ERV as energy recovery ventilation, but in this way, it only means that energy recovery as temperature and humidity recovery, both then together. The main idea of ERV systems is to exchange the energy contained in normally exhaust air of a building or then the indoor air, and this is then used to treat the incoming outdoor air. If we think about this, that from thermodynamical perspective, the warmer body always gives away the heat to a colder body, or then the energy is always given to the body that has it less. Then during warmer season, the enthalpy recovery system, it tries or it helps to pre-cool the air that is entering the house, and it dehumidifies it. This is only happening or functioning when the bypass is not activated, and therefore the air goes through the heat exchanger. During the colder seasons, that is usually brought as an example when we are talking about heat recovery ventilation, is that we have water that is heated and we are using energy for that, and therefore there is no reasonable solution or way that we would just let that energy to go out of the window, because we also want to have fresh air inside of our house. Then we are using heat recovery to use that energy, what we have already used, to heat the house. And with this, we are heating up the cold outdoor air. So the heat exchanger is working as a preheater. And also with enthalpy recovery, we are humidifying this outdoor air, because in winter times, Central Europe and in colder regions, we have problems with too dry indoor air because the heating is drying up the air. And using enthalpy recovery is one easy and simple way how we could use the humidity that we are producing indoor, for example, commercial cooking, that we do not just, let's say, ventilate it outside, but we can still have it in our living rooms and areas. Said that, then we also have to keep in mind that when we are talking about energy recovery ventilation or enthalpy recovery ventilation, then this is where we are recovering temperature or the heat and humidity. When there is HRV, then this system is only recovering heat, but no humidity. And when we are comparing the ERV and HRV, then it's also all the time people want to see numbers and to see the comparison there. And in this slide, we have the comparison for Zehnder Comfort Q 350 with different heat exchangers, with HRV and ERV. And the results brought out here are taken from the Passive House certificate. Passive House Institute is an independent lab and research center where companies can send in their ventilation units so they could be tested in an even and comparable test environment. And the results there are then comparable between the ventilation units between different companies and producers. The results that you can see on the slide are taken from the certificates for cool and temperate climate. We also have certificates for very hot climates, and there, instead of heat recovery, you can see the cooling recovery results. Comparing these results here, when we check the heat recovery rate for heat recovery ventilation, we can see that it's 90%. And for enthalpy recovery ventilation, it is 86%. So in this comparison, we can see that heat recovery ventilation, HRV, has higher value than the ERV. But in addition, ERV is recovering also the humidity. And when we compare the total energy recovery, which is sensible heat, temperature, and something that we can feel, and latent heat as the humidity and also sometimes called as the hidden heat or energy, then the total recovery rate for ERV is higher. And to kind of bring up this example a little bit more, or to describe this solution in another way, is that like one of our colleagues example of the apple picking. For example, if we have a company that is packing apples, we have a worker A who is picking only red apples, and he or she can pick 9 apples out of 10 and pack them nicely. And then we have a worker B who can pick 8 red apples from 10 apples and additionally 7 green apples. So all in all, in the end, in that comparison, which worker is more efficient? The one who can pick only red apples or the one who can pick red and green apples? So that's, in my opinion, a very good and nice explanation or similar comparison if we are talking about different heat recovery possibilities, or sorry, recovery and heat recovery possibilities. Yeah, and here is the nice, also if we are continuing with the comparison and descriptions, then relative humidity and absolute humidity. It is that the absolute humidity is showing the water content in the air and is usually expressed in grams per cubic meter. And relative humidity is the ratio of the current absolute humidity of the highest possible absolute humidity, and is something that is described in percentages. If we are looking at those 2 containers on the pictures, and there is one container that is 60% full and another one that is 90% full, then the question would be that which container has more milk in it? And here we have prepared a small poll So please pick your choice. If you think about the pictures of the containers, in your opinion, which one of them had more milk inside? Let's give a little time to answer. Okay, we have 57% of the participants have voted. And let's wait a couple of seconds more if we can get some additional votes. And Adrian, could you tell us what is the right answer in this?
Yeah, sure. Thank you, Piret, for the introduction. Now I'm taking over, and I can see that a lot of you took part at this poll, and actually the results are quite clear. 80% say the 60% full milk has more milk in it, and 20% say 90% full has more milk in it. So actually, yeah, I need to say that this was a trick question. Actually, the right answer wasn't given because without knowing the volume of the container, you cannot answer this question. So everybody who did not make a choice was right. So 10 points for them. Let's have another try. Now I'm asking you which air is more humid, or which air contains more moisture. Air with a relative humidity of 50% or air with a relative humidity of 70%. And now I swear this is not a trick question, so everybody can take an answer. Okay. Some more seconds. Okay, yeah, you are totally right. In this case, you need to know the temperature of the air to make a statement. So I was just asking you these questions because I want you to think about the terms relative and absolute humidity and to get you on board for the next few slides. So let's move on. Let me talk about thermal comfort. The temperature that we feel, the perceived temperature, is not only depending on the temperature itself, but also on humidity and the air movement. So at this point, I want to introduce the humidex factor. Humidex is standing for humidity index, and it shows the higher the humidity, especially at high temperatures. So when it's very sultry, it's very stressful for our human body, for the human organism. So what you can see in the chart below, we have 26 degrees in all 4 cases. In the first one, we have 30% relative humidity. And at this point, the perceived humidity is 26 degrees actually. If you look at a relative humidity of 60%, we perceive it or we feel it as 32 degrees in that case. So here you can see this correlation. But this is also the other way around. When the air is too dry, it doesn't feel comfortable either. Dry air causes cough, eye and skin irritations, and very important in these times also the transmission of viruses and bacteria is on a high. The indoor climate is very dry. And that is due to the fact that there are more particles in the air, there's more dust where these viruses can lay down. And also we human beings receive that particles better when our noses are dry and our mouth is dry. So the infection rate is higher when the indoor environment is dry. So, you know, humidity, or I should rather say water, is the basis of all life, so to say, for molds and bacteria as well. But we do not want to have, because they damage our building structure and they also cause health complaints at the building occupants. But where does this humidity come from? It comes from people, washing, cleaning, when we take a shower, or also plants are producing humidity. On average, every day, a single person produces 2.5 liters of water a day. But what do we want to have? Which humidity level? In our regions, we have cold winters, so there the humidity tends to be very low when we heat up our buildings. And in summer, when it's hot outside, we need to cool down our buildings. There, the humidity tends to be very high, and this doesn't feel comfortable either. So the humidity needs to be considered in thermal comfort zone lies between 40 and 60% relative humidity. And it also needs to be considered to prevent structural damages. And yeah, you can see this also in the chart on the left-hand side. There you can see the concentration of bacteria, virus, fungi, respiratory illness, allergies, and asthma in terms of humidity. And luckily, this optimum range is equal to the thermal comfort. So here we are also at 30% up to 70%. On the right-hand side, you can see an example what happens when the air is too humid. There arise molds, and they cause health complaints, and they also damage the building structure, as you can see here. And studies showed that these mold fungus arise when the humidity is at 80% over a few days. Yeah, at this point, I want to show you a short video about our Enthalpy heat exchanger, where they show how it works and what are the benefits.
We spend 90% of our lives indoors. Our lives have become a complex mixture of commuting, indoor work, and indoor activities. To save energy, we have insulated our houses so well that the rooms do not get enough fresh air. Fresh air is obviously best for our health. On cold winter days, the air indoors is often too dry. This can lead to unpleasant irritations, dry skin, red eyes, or even health problems. On hot summer days, on the other hand, the warm, humid air feels even warmer than it actually is. Fresh air and relative humidity in a comfortable range between 40 and 60% are best for our well-being. The answer? A comfortable indoor ventilation system with humidity recovery. It enables optimal indoor air quality and is a healthy and energy-efficient alternative to opening windows. Zehnder's comfortable indoor ventilation system with Enthalpy exchanger recovers up to 80% heat and additionally up to 70% of the humidity. So, in the winter, it retains heat and moisture inside a building whilst providing the right amount of fresh air. In summer, on the other hand, heat and humidity is extracted from the warm, humid outdoor air before the fresh air enters the house. Zehnder's patented polymembrane acts as a separating layer for the airflows. At the same time, it prevents transfer from impurities and odors from the extract to the supply airstream. This energy-efficient process prevents the indoor air being too dry in the winter and too humid in the summer. This gives you the best indoor air quality for even more comfort and well-being. You can feel it whenever you enter a room that's using Zehnder Comfortable Indoor Ventilation. You already have a Zehnder Comfortable Indoor Ventilation system and would like to extend it to humidity recovery? You can simply upgrade to the Zehnder Enthalpy Exchanger. Your Zehnder partner will be happy to advise you. Zehnder, always the best climate.
Yeah, okay, now you got some insights, but we will go more into detail now. So here you can see the HX diagram. Before we start, I would like to point out the different air streams we have in a ventilation system and what are their terminologies. So if you look at the right bottom corner, you can see a house, and there we take in the outdoor air showed. Then we are going through the heat exchanger or the enthalpy exchanger and supply the air to the apartment, the so-called supply air in red. On the other side, we take out the extract air going through the heat exchanger and blow it out as exhaust air in orange. Now let's get into the HX diagram. Here you can see a red shape. That red shape shows the comfort zone. So starting at 20 degrees, going up to 26 degrees at a relative humidity level from 30% up to 65%. Yeah. So now we start with the standard heat exchanger in the winter case. So what you can see here is that we take in the outdoor air at a level of 0 degrees and a relative humidity of, and the absolute humidity is 3 grams per kilogram dry air. So now we are going through the heat exchanger and we recover the heat from the indoor air. So we heat up the air to 16 degrees. We are just going straight up. So there's no change in the absolute humidity. We still have 3 grams per kilogram dry air. And what you can see now, we have a relative humidity of maybe 28%. And we are out of the range of the comfort conditions. So what we do now, we have 16 degrees. We heat up the air with our central heating system. So now we are going up to 20 degrees. And if we do not have any internal humidity gains, there are still only 3 grams of moisture in the air. And then we would have 20% relative humidity, which is too low. On the other side, we can see what happens on the extract air. We give the heat to the supply air. The extract air is cooled down, and actually we reach 100% of relative humidity, and there condensation takes place. So if you are using a standard heat exchanger, you also need a condensate drain because you need to get out the water of the unit. Yeah. Now let's take a look to the summer case. We have the outer air here, and we just cool down, or we just recover the cold from the indoor air. And so we have 24 degrees and a relative humidity of 70%. Yeah. So this is very humid and not comfortable. We are still not in the comfort zone. If we want to get in the comfort zone, we would need to dehumidify the indoor air. So now we take a look what happens if we are using an enthalpy exchangers. They are still the same conditions. So same terminologies, same local conditions. It's the same house, but we just change the HRE with an ERE. So what happens in winter is we have 0 degrees outside, 3 grams per kilogram dry air, absolute humidity. And what you can see now is not only a shift in the vertical way, but also in horizontal way, because we are also recovering moisture. So you can see we have now a relative humidity of 50% at a supply air and a total content of 5.5 gram moisture in the air. So we have a difference of 2.5 grams. And if we would now heat up the air with our central heating system to 20 degrees, we would hit the comfort conditions. So we were in this comfort shape. And what we can also see here is on the other side that we do not have a condensation formation. So this is why our enthalpy exchanger or our enthalpy versions do not need a condensate drain. What happens in summer? We have the same effect. The humidity of the outdoor air is going to the exhaust air, and we have a less humid supply air. And here actually we are already in the comfort zone just by using a enthalpy exchanger. Yeah. Okay. So let's gather all the benefits, firstly during the colder season. First, I would like to point out the main advantage, and this is that we can provide with an enthalpy exchanger a very comfortable indoor climate because we avoid dry indoor conditions in winter. The ERE increases the inside relative humidity round about 10%. This was tested in field studies, and if you imagine a typical airflow for apartment or a small single family house, this 10% would be equal to 4 up to 8 or 9 liters a day of water, which you can recover. So if you imagine that amount of water, I think it's quite a lot. You also avoid condensation formation because you recover the humidity. There is nothing to condense when you are using a ERE. So you do not need a condensate drain. And what is also important, you have a higher recovery efficiency because the condensate, which occurs in the standard heat exchanger, blocks the heat transfer. So if there is condensate, you do not have the full recovery rate. So you do not only have a higher recovery using an ERE because of the use of sensible and latent energy, you also have a constant recovery efficiency. And Another important point is that the ERV is running till -6 degrees. The HRV, in comparison, is only running till 0 degrees. This is due to the recovery of moisture and heat. So below these temperatures, you would have the risk that the unit is freezing, and when this leads to damages at the unit. And to avoid this, we have an additional preheater. So if you are in a cold region, you need a preheater. If you still want ventilation below these temperatures, the preheater, as the name already says, preheats the air which is coming into the unit, so that there's no risk of freezing. Logically, the preheater, which starts at 0 degrees, has a higher electricity throughout the whole year than the one who just starts at -6 degrees. Now we take a look at the benefits during warmer season. Firstly, the main advantage is also the comfortable indoor climate, which can be provided using an ERV. In summer, the ERV decreases the summer inside relative humidity, as you have seen in the HX diagram. But what we also have in warmer climates is a lower consumption for the active cooling system. Why is that? Because in the total cooling output is equal to the sensible cooling, which relates to the temperature drop, and the latent cooling, which is the absolute humidity drop. And you know, dehumidifying the air is very energy intensive. So when less humid air flows into a cooling system, which you have using ERV, less effort goes into getting rid of the humidity. The result is a higher temperature drop. And this is what you actually want to have when you have a active cooling system. So you can see it also in the bars below. There you can see that with a less humid air, you have a higher temperature drop with the same effort. So the ERV reduces the power consumption of an active cooling system. Let's also talk a little bit about the maintenance, which is equal for both exchangers. You just need to open the unit and then you can remove the enthalpy or the heat exchanger. By the way, they also said it in the video, if you want to upgrade your unit, this is simply possible because you can just change the HRV to an ERV. There's nothing else to do. You just need to confirm in the unit setup that there is an ERV installed now instead of. So yeah, coming back to the maintenance, we recommend to take a look at the heat exchangers when you are doing your 6-month cleaning procedure, and you just look on the heat exchanger if there's anything abnormal. Otherwise, if there's nothing special, you can just leave it like that. We recommend, or you should clean the exchangers on a 5 years interval. And how to do this? You can just do it with hot water. Take a container, let hot water into it, but this hot water should not exceed 40 degrees Celsius. And then you can submerge it several times, rinse it, and shake off the excess water, and then you can put it back into the unit. For this procedure, please do not use aggressive cleaning agents or solvents, because they could damage the membrane. The lifetime of the heat exchangers depends on the local conditions and how well you did the inspecting and cleaning, but in general, we say that they have a lifetime up to 15 years. So now we have spoken a lot about the differences between heat and enthalpy recovery and what are the benefits of enthalpy recovery. And at this point, I would like to hand over to Ryan because he can explain to us how this exchanger, how the membrane actually works. So Ryan, I give you the presenter rights and then you can go on. There you go.
Okay. Hi, everyone. Great. Here we go. Hello, everyone. My name is Ryan Heising. I lead materials research and development here at Core Energy Recovery Solutions. I'm located in Vancouver, Canada, where our membrane and exchanger production facilities are for North America. And today I'm just going to have a brief introduction to the membranes we use in ERVs, including the Zehnder ERV systems. Here we go. So I think we've already talked quite a bit today about how an ERV works and what it does. Essentially, what we are doing in a ERV is passing exhaust air from a building over one surface of a membrane material and passing the supply air from outside over the other surface of a membrane material. And so the membrane is preferentially transferring both heat and water vapor, and blocking the transport of gases and contaminants transferring between the airstreams in the buildings. And this allows the ERV, as discussed, to use the exhaust air to pre-cool and dehumidify the incoming air in cooling mode, so in Northern Hemisphere summer conditions. And it uses the exhaust air to preheat and humidify the incoming air during heating mode in Northern Hemisphere winter conditions. The ERV and the membrane are a passive device, and so moisture and heat transport are occurring via the concentration difference between moisture in the airstreams, or absolute humidity difference, as well as heat is being driven by the temperature difference. So when we're designing membranes for these devices, and you can see here that we have a picture of a cross-flow ERV core, which is largely what is sold in North America. But the principles are all the same with the cross-flow and counterflow. When we're designing and making membranes for these devices, what we want in a membrane material is very high rates of water vapor permeability So the ability to transport a lot of water, which leads to high latent effectiveness in the exchanger. But we also want what we call good selectivity. So we want water vapor to transport, but we don't want any other gases, contaminants, volatile compounds that are in the indoor air or odors to be able to transfer through the membrane material. So we have to make the membrane selective for water vapor over other gases and contaminants. We also want a number of other functionalities in the membrane. It needs to be antimicrobial so that fungus and bacteria cannot grow on it. We want it to be freeze tolerant in case there are incidences of frosting a long lifetime. And in the presence of condensation, the membrane must also be stable to water vapor or to liquid water. And so our approach at Core is to make what we call a composite polymeric membrane. And what this means is that we have a microporous support layer onto which we apply a very thin but dense polymeric coating that blocks the transport of gases and VOCs, but allows the absorption of water into that material and the diffusion of water through that material. And so by having this composite layer, we're able to make that very thin layer and have high water vapor transport. Due to that dense polymer layer on the one surface, we have no pores in that layer, so it provides a very good barrier to air and contaminants. And this also allows us to make a material that is very dimensionally stable in a wide range of conditions, which adds to the durability. Furthermore, we have antimicrobial function in this membrane material, which blocks the growth of fungal species and bacteria. And I'll touch on just a minute later as well, due to the nature of the material, we also have blockage of viruses through the membrane. We can look closer here, and so what we're looking at is a cross section of the polymeric membrane that we produce. This is about 100 microns in thickness, which is about the thickness of a human hair. And what we're looking at here is mostly the microporous layer. And if we zoom in to the surface, here we can look at just the surface layer, and so we can see we have a very thin but dense, so non-porous barrier layer on the surface of the membrane. And so that barrier layer preferentially absorbs, it's made of a polymer that preferentially absorbs water vapor over other materials, and so allows the water vapor transport, but since it is dense, will block the transport of gases as well as any sort of other contaminants that are in the air. Oops. And I was asked just to touch on in these times the viral blocking aspects of our membrane. When we were developing this, when we had developed this material, we had done some tests quite some time ago to just confirm if any of these type of species can pass through the membrane. What we had done at the time was to just send the membrane for a test that is used for medical garments. And so this is just a test of can viruses penetrate and pass through a material. And so as I discussed, we have this dense film layer and a microporous substrate layer in our membrane material, both of which would block the transport of anything that is of the size of COVID-19, which is around 125 nanometers. And so in this viral penetration test, they use a surrogate material or a surrogate biological contaminant that's about 25 nanometers in size. And so in our testing, the membrane materials were tight to the transport of these surrogates, which are smaller than COVID-19, and block the transport of viruses. And so a membrane-based exchanger can allow separation, complete separation of air streams in which the membrane will not allow the transport of viral species as well. And so I think that concludes my portion of the discussion here, but thank you.
Yeah, thank you, Ryan. And thank you also, Adrian, for the technical perspectives and all this. Also for Ryan, thank you for specifying how and from what materials the heat exchanger is from, and the research behind it and the tests that have been done to prove the quality of the product. And with this, it's time to make a summary of our webinar, and to wrap it up in the topics is that the benefits of enthalpy recovery ventilation. What we heard about is that it provides comfortable indoor air climate, avoids dry indoor conditions in cool climates, and also avoids humid indoor conditions in hot climates. In that way, that in addition to the heat recovery and the comfortability with the temperature, we also can influence or affect the humidity that we have in the room. Avoids condensate formation for high efficiency in practice. So we have also field tests and evaluate the results. In that way, we have functioning systems where we can prove that the condensation formation is reduced. Also, there is the lower power consumption for defrosting, as Adrian brought out. Then the temperature for the heat exchanger when it is, let's say, a moment of threat of frosting, this is taken into a lower level because we are taking the humidity and therefore the water away from the heat exchanger, and we can start the defrosting later and therefore save the energy. And also there is the benefit of lower power consumption for active cooling system, that as again there is less humidity in the air that we would need to dry out and therefore save the energy of the cooling system. And with these points, we would also like to move forward to the topic of our next webinar. In the series, the next topic is passive house certified ventilation units. If you can see the QR code in the bottom of the slide and you have your smartphone next to you, then by scanning the code, it will already take you to the page where you can register for the next webinar. So it will be an easy and fast solution. Of course, we will promote the event in social media in the beginning of December again as a reminder. But if this topic seems to be interesting for you and you would like to hear more about the Passive House Institute, then the requirements to receive the Passive House certificate and also the ventilation units and what it has to meet up, what expectations, then this would be an interesting webinar. It is held on 10th of December, that is Thursday, and it will begin at 1 p.m. Central European Time. And yes, therefore, I would also like to say thank you all for participating and for watching our webinar, Enthalpy versus Heat Recovery. I also would send big thanks to my co-hosts in that way, Adrian and Ryan, thank you. And as we still have a little bit of time, then if there would be any questions that we could have the time to answer, then please feel free to send them to the question part. Or if the questions will come up later, then of course you will have the contacts on the slides provided here, or it will be possible to get or send the questions to your contact in Zehnder to us, and we try to answer them as fast as possible. I would also like to say this, that when we are closing this webinar, then we have some questions as a feedback for today's event, so that it will take maximum 1 minute. There are 3 questions with the feedback, and we would appreciate a lot if you could take that time to answer the questions. Yes, so.
Yeah, there's one question. Are the condensation pipes still needed for ventilation units or not? So for the HRV, you still need a condensation pipe. For the ERV, you do not need a condensation drain. That would be the answer for this question.
Yes, so we have questions here as well, that that how does the bypass work with ERV during the summer? Then it is that the bypass is activated based on the temperatures, and that this is just something that the unit is controlling itself, and the temperature level can be changed by the user of the house. So usually it is in a way also that in the summer time, in the daytime, when the temperatures are really much higher outside. Yes, actually a good question, because it is that then there should be, the bypass should be open a little bit, because then we would have the, let's say, energy recovery or then cooling recovery available. And then for it during the night time, the bypass clamps are activated, so the airflow through the heat exchanger is reduced in a way that we don't have the heat recovery. In that way, we can use this like passive cooling, or like, let's say, this ventilated cooling during the night time. And yes, but I would specify this question in what temperatures we can set this and how this can be changed. Yes. So here, and then there is also a question that what happens when the humidity in the house is already over 70 to 80%. It is also in that way that the ventilation unit, this is usually in the cases when, for example, someone is taking a very, very long shower and the overall humidity level is rising, then it is possible to put the say the ventilation into boosting mode, that we would reduce this humidity from the house by making the air exchange with the faster rate. But this is also in the case when the unit recognizes that the outside humidity level is lower. But if the outside humidity level, for example, is similar, then the unit will not allow to start this boosting mode.
Yeah.
Okay. Seems that we still have some here. Okay. I must say that with some of the questions here, is the percentage by which the latent heating in winter can be estimated. For example, a 0 degrees Celsius at relative humidity. This is something that I would not be able to answer on spot right away, and we will need to do a little bit investigation to get the right information. But it is that we have all the questions here that we can take out, and we can then afterwards also send the answers separately via email. So yes, that in this way we should be able to answer questions that are still unanswered here. But as we are today, now the time has unexpectedly run up, then it is that the questions that we were not able to answer now, or where we have not been able to read out until now, we will take you, or we will contact you separately and answer them. So that said that, I would say from my side, thank you for participating, and wish you a nice evening or a day, and then hope to see you soon in our next webinar.
Yeah, thank you. Goodbye from my side.
Thank you, everyone.